Okay. Okay, start us off here, get our brains thinking. Okay, we're gonna take your hand for me and lift it up in the air like so. Either hand, your choice. Okay, now reach down and feel the leg of your chair.
With the same.
With that hand.
Chair or.
Chair leg.
I see. Which one?
Any leg. Okay, feel it. Notice what you feel. Okay. Now take your hand off. Now touch the top of the table. Okay, turn to your neighbor and describe what you felt. Ready, go.
So basically,
like a round.
There's a point to this, I promise.
it felt but not as. In fact, this thing was there's always something that has to do with what we did. I don't know. Table or basically decorated the wood.
Okay, we'll come back to that in just a moment. Okay, so the first thing we're going to look at here, everybody, as we get into talking about chemical reactions, is this unit, the first part is about the energy that goes on within chemical reactions. So this graph right here is known as a reaction pathway diagram. What it shows is it describes the energy and how it changes as a reaction progresses. So there's a few things with these graphs we need to be able to do. Number one is we do need to be able to label them and what the different parts are representing. And then the second part is we'll learn what the numbers represent. Okay? So the first thing is the starting point of any reaction, so label this with me, is always represented of the energy of the reactant. Okay, so remember that reactants are the things on the left side of the arrow. Okay, and this energy represents how much energy they have already. Because everything has a certain amount of energy, because energy is movement, and everything moves to some extent, right? So these are the reactants. As the reaction progresses, energy can change. In this case, the energy goes up, and then the energy goes down. And so the end line always represents the energy of the products. Okay, so for our graph here, if you needed to label, so right under or off to the side of your graph, we have E of the reactants, which would equal, in this case, 100. Typically, the energy unit we're going to use in chemistry is actually a joule, so we represent it by capital J. You can see that right there. Okay. It's just a unit of energy. There's lots of different units of energy. We'll talk about more of them in other units. But for this unit, it's a joule. But joules could be related to volts. Like batteries are measured in a voltage energy. Joules are just like a volt, but just a different unit. It actually even can be converted into calories, which is our energy unit that we eat. Right? But technically, a cereal box could be listed as a joule. Or someone once mentioned, like, well, that'd be fun. We should list our cereal boxes in volts. I used to be like, how many volts am I getting with this energy, right? But it's all just a way of representing energy. Just like how with length, right, you can measure in inches or centimeters or a mile. Like, they all represent length. Joules, calories, volts all represent energy. Okay, and then our energy for our products would be about what? Same thing again. So energy for product, same thing. You just go to where the products is, match it up, which, once again, it's a rough estimate when it's a graph, so it's about 160. I guess we can get more accurate, but we'll just do that. Okay? The next thing on our graph is the highest peak. Okay, the highest peak of it is known as the activated complex. Okay, so the highest peak is the activated activated complex. So for this one, take it over is about 220.
Do you look and you can just add 1 to 26 because it's saying the tops are 21.
Okay?
Yes.
Now once again, with your answers on your homework, because you'll be given a graph and interpreting, there's like a range of what's correct because obviously this isn't the most detailed of graphs, right? So there's like a rate within a range. That's why I kind of just rounded our answers, even though they could be more exact. Okay, now what the activated complex is, it's the point in the reaction. You can kind of see it better on yours because there's little pictures of molecules. It's the point at which the bonds of some start breaking and new bonds start forming. So kind of like some of these Legos start unlinking and they start linking together, but it's not quite finished yet. It's a very unstable position. Just why, like if you imagine the top of a hill, like a golf ball on top of a hill, is not at a stable position because it can easily roll both ways. So it's a very hard thing to isolate. Like those things don't really exist because it just goes one way or the other. But it's kind of that point at which things start changing in the reaction, okay? All right, the next two important pieces, so this is our activated complex. Okay, the next two most important things on our reaction is number one, what is called the activation energy. Let's see, there should be, because you have a little blank to fill in. Oh, that was all there. Okay, so the activation energy, you have a little blank right below it, okay? And there's a little box where we can fill in this equation. The activation energy is the energy that it takes to activate the reaction. Hence the name, activation energy, okay? What it means is it's the minimum amount, okay, so that's what that blank should say is the minimum. It's the minimum quantity of energy needed to make it happen. Meaning if you don't have that minimum energy, then the reaction won't go. As long as you supply the minimum energy, then it will happen. A great example of activation energy is that's what you do when you put your keys in your ignition and you turn it, is it causes a spark to ignite the gas, which then allows the combustion to begin. Right? That is the minimum amount. It's not much. Your car doesn't need much energy to get going, but it does need a little spark to make it happen. Okay? So the higher the activation energy, okay, so the higher this difference is, then the more energy that's needed. Or so we have very low activation energy, then it doesn't require much to happen. So notice that the activated complex is the very top. Activation energy is the difference between the start and the top. So you have to do just a little bit of math of minusing the very top to where you started. Okay? So for our reaction, once again, they already have it listed here. So E of A is the symbol for activation energy. And so it's 126 is what they, based off our numbers that we wrote down, what would it be? 120, right? Because we said 220 and 100. So questions on calculating the activated energy? Okay, the other measurement on here is what is known as the change in enthalpy, which is symbolized by this triangle H. For those that haven't learned in math before, the Greek symbol delta, so it's a triangle, but it's known as delta, is the symbol for change. So anytime you're measuring the change of something, you'll see this triangle and then whatever it is. So this represents change in enthalpy. Okay, enthalpy is the amount of energy that is released or absorbed total. It's the net change, okay? So in this reaction, okay, up means energy in, down means energy out. So you have both, but the enthalpy is the overall net change combined. Okay, so it's the difference of the products to the reactants is what the enthalpy is. If it kind of helps because it's an H for the symbol, it's kind of like the heat. And that's what we're going to get into next is heat out versus heat in. So if that kind of helps, if you want to define next to enthalpy, kind of say like, okay, this is the heat of the reaction. If heat is going out or heat is going in as the overall net change. Notice that you always have both in terms of the progress, right? Because the hills always go up and they always go down. But the net change is what the enthalpy shows us in the end. So for our reaction, what did we say? 160 is that we said our products were?
Yeah.
So we would do 160 minus 100, so our net change would be 60. Now notice that the sign of delta H is going to be extremely important because it helps you know, did more energy go in, which in this case it did because it's a positive value. If it was a negative value, then that would mean more energy actually came out in the end. Okay, questions on those graphs so far? Okay, so now what we're going to look at is just the two types of classifications for heat out and heat in. And that's really our objective today, is that given an example, given a reaction, can you identify, all right, is this an overall net out or overall net in? Okay, so the first we're going to talk about is an exothermic reaction. Exothermic reactions are an overall energy coming out. Okay, the way I remember it is because X, like exiting, so the heat is exiting the system. Okay, now we're going to look at a lot of different scenarios of how you can identify an exothermic reaction depending on what's given. Let's go back to our chair really quick. Okay, so when you touch, and this very slightly dependent on the individual, but when you grab the leg of your chair versus the top of the table, how would you describe the temperatures of those two surfaces?
The same.
Kyle says the same. Who agrees with him or disagrees with him?
So the metal is colder.
Brian thinks the metal's colder. Let's do this. Ready? Raise your right hand if you agree with Kyle.
Yeah.
Raise your left hand if you agree with Brian.
I'm not going to
You
do
guys
either
should agree
because
with
I
him
don't have
because
left hand.
technically
And I don't agree with this. This is discrimination.
That's not
What?
Raise your right arm if you agree with Kyle. Raise your left arm if you agree with Brian.
You should raise your right.
You walked into that. I know you did.
I did. You got me there, Seth. Okay, you gotta raise one because it's either yes or no. It's either the same or they're not the same. There's no in between them, same and not same.
I wasn't listening to you, so I'm just.
Praise be.
You should raise your right hand. It'd be cooler that way.
Okay, I see a lot of left.
Let me explain.
Okay, let's hear our justifications.
Okay, so basically the metal is more dense, and the molecules are going to transfer heat faster, so you're going to feel the heat difference a lot more, but they're actually the same temperature.
So Kyle's actually right, but I don't blame you guys for agreeing with Brian because of how it feels, right? It feels, typically this works, sometimes it doesn't work depending on the person's hand. But typically metal will feel colder than other surfaces do, or vice versa, right? Like in the summertime, and you get in your car and you touch your seatbelt, if you touch the metal part, it's like death, right? Because it's so hot. What?
She comes back to this.
There. Is it still You'll take over for me? Perfect. See ya. I'm ready to go. Joe? She wasn't.
Did you get a ride to school or
Did you see her somewhere else?
Yeah, quiet. Somebody last minute.
Oh, really?
Quiet.
Okay. So, what's going on here, everybody? So, number one, the way we know they're the same temperature is because they're in the same space. And whatever space something is in, as long as it's not living, okay, because living things obviously produce or take in energy, but if something is not living, everything else in this room is at the exact same temperature, and that's the temperature of the room. Because heat has this magical thing of always flowing in a direction to become equalized. Now, the reason why they feel different to us is because of the direction that the heat is going. Metals, like Kyle mentioned, are very good at transferring heat rapidly. Okay, the way I think about metals is metals are very good heat suckers when it's cold, or heat pushers if it's hot. So when you're, so everyone grab your hand, grab your chair. Okay, feel this happen, ready? This is so cool. Okay, so as you're holding the chair, okay, and it feels cold, if you keep your hand there for a while, does it still feel cold? I mean, depending on how cold your hand is, but like the longer you keep it there, it doesn't feel cold anymore, right?
It feels like the same warmth as your hand.
Because what's happening is the chair is sucking the heat out of your hand.
That's real.
They're very good heat suckers to equalize the energy. Vice versa, if a metal is very hot, it's doing the same thing, except now it's throwing heat into your hand, which is why you get burned if you touch hot metal, right? So one thing you need to understand from a scientific standpoint is that cold does not exist. There's nothing that measures cold. Cold is just the absence of heat.
Cold doesn't exist.
Cold doesn't exist. There's
Cold is
nothing
alive.
tangible that is cold, right? So let's go back to our exothermic reactions. An exothermic reaction is a reaction that releases heat outward. Now, the trickiest thing with what we're going to practice today here, everybody, is when heat or energy is flowing, heat in or heat out, it's all about the perspective of what you're focused on. So you have to make sure we have what we classify as the system versus the surroundings. If you identify the wrong system, you might be right, but you're going to be opposite of what it is. So for example, with our chair leg example, if the chair is the system, the chair's energy, what's happening, is it going into the chair or out of the chair? When you're grabbing it with your hand, which way is the heat going? Into the chair. So if the system is the chair, heat is going in. If the system is your hand, where's the heat going? Out. So you have to make sure when we're looking at these, because it's just opposites, that we focus on what it is. So when we say that a reaction is exothermic, we're saying that the system is releasing the heat. Okay? So first off, in terms of a chemical reaction, what that means is that the products will have less energy than the reactants. So all exothermic graphs will have lower products than they do reactants. You'll have more down than you do up if it's exothermic. Okay? Another way to identify it is that energy is a product. So what we're going to start seeing is that when you write a balanced chemical equation, like this one, so write this as an example right in that little box right there, okay, is we can start including energy in a reaction to help us explain more about what's going on. So if energy is on the product side, oh, you don't need that one, Hattie.
Oh, okay.
You're good, thanks though. If energy is on the product side, that would be classified as an exothermic reaction. So go ahead and write that down in the box there. Now, there's two ways in which energy can be in a reaction. Sometimes they just write the word itself like so. The other times is you can also write the actual value of it, meaning how much energy. So you could have also said instead of plus energy, you could have also seen like plus 270 kilojoules or whatever it is. So that's the other ways that sometimes we just write the number itself. Now going back up here to the reactions, if the products always have less energy than the reactants, that's going to mean that the delta H, the change in energy, will always be negative. So another way of identifying if something is exothermic is if you have a negative delta H, a negative enthalpy change, it means it's an exothermic reaction. So on your homework today, what you'll do is you'll kind of practice, given various ways, if something is endo or exothermic. And we'll do a few practice problems before we get there. But okay, so now let's look at the opposite. So the opposite of exothermic is endothermic. Right, once again, to help me remember, I think N as entering, X as exiting. So endothermic reactions means it's absorbing the energy, it's taking it into the system. Okay, reactants will always have less energy than the products. So these reactions are going to have a positive delta H. In terms of a balanced chemical equation, the energy now is going to be a reactant. So it's going to be on the left side of that arrow. So write that down as an example. And then same thing with that energy. Sometimes they write it as a word, but it could also be written as a number. So they could have said this plus 150 kilojoules turns into this and that. And then going back to the graph, recognize that endothermic graphs are always going to end higher than they started. So, questions so far on the difference? Yeah. Most likely, I'd say most likely. Pretty much, you know, if you ever see big coefficients already, then it's probably already been balanced for you. So yeah, a good question, Barnard. Other questions so far? Okay, for some smiley faces, and then we'll practice it on the homework list with you before. I'm gonna give you let's do this one, and then we'll do some endo and exothermic. This didn't get printed on the notes, so you can just either write it down somewhere else or just answer it. I don't know, you can write your answers at the bottom and help you remember what they are. So try this out with your table buddy, and then we'll check it. I just have to run. I realized I didn't get my copies of your homework, so I gotta go grab that and copy set it really fast.
Basically, because the product is going in and the reactants it absorbs. So now it's endothermic.
When did you have it last?
Saturday.
Was that your house?
No, it's
Oh, you had it here Saturday.
The truth is that
Day
Also, you coming tonight? Tonight's closing.
this one's like 120.
like 2 of
Very disappointed in you, coach. I'm quitting somebody. Just kidding. I don't think it works like that.
We all fit those out.
Okay, yes, you're good.
So,
Even way
We didn't even go to the ag subject.
I'm trying to get over and I still haven't gotten over it. So my grades are not doing so well in a lot of my classes. Could I come in for scheduling just work on nothing more? I'll get like the that we've been doing and ask for help. And then I did the last instance because I was the one that started the lab. So I decided
That's just the only one who did it.
today after school I have to take the math test and the bio.
Yeah.
Okay.
Yeah, I mean, obviously you have a lot to get caught up. Sooner is always better, but
Yeah. Thank you.
I got a lot of which one?
Okay, so now you apply that like the reactant to the activated complex.
What is the energy content of it? And the products is on this. This is only the reactant.
This one I can go on diving.
Go with ritual.
So that would be 60.
It was just all. And then now I just bought like a
Is the reaction
That's all I ate.
Did it already answer? Wait.
Minus
Especially something is the A and thermic,
North, part one.
exothermic. discussion was the reactants, which is on the bottom of the and then 7 is the here.
Okay, everyone ready to check it?
Oh, the EA, right?
Those thermometers can register, right? Okay, so for everyone, so 1, 2, 3, 4, 5, 6. Everyone that you get right, you can have a smiley face.
Oh, yes.
Oh, so everyone is higher at Endo or Exothermic.
So what is your question for?
I'd say that's endothermic reaction, right? Because it's higher energy.
Yeah, because the molecules, the energy of the product is higher than the energy of the reaction.
That's what I was thinking.
Yeah, the very last page of your notes is blank if you didn't find that. So that's right, the answer's down.
Synthesizing.
Yes.
We're so good. We're literally
Today.
They're so cool.
The only one I can do is combustion and synthesis. I don't like decomposition. Actually, decomposition is not that hard because it goes, it breaks everything. But I hate double replacement and
Have you got a what?
Yeah.
Okay, is everybody ready now? Yeah?
Yes.
Okay. Now once again, this graph's pretty straightforward. There is some variance in terms of like if you're close to the same number I say. Okay, so the energy content of the reactants you should have put 20.
Dude, that's a smiley right there.
No.
The reactants are the starting line. Okay. Alright, energy of the activated complex, you should have put about 120.
Dude, that's what I put.
That's fine, yeah. I don't even know, I guess it's set over here, but joules. Alright, products, you should have put 80.
Wait, that's number 7?
For number, yeah, I don't know why the number is so weird. That's number 6.
Oh, okay.
I was gonna say no, that's
Number 6, the products. Okay, stop me if you don't get it right and you don't know why.
I got them all right.
Okay. Alright, you should have said the reaction. Let's do this actually just so I can see
Is
before.
it everyone you get right, you get a smiley face?
Okay, this is the sign for exo. You're making an X. This is the sign for endo. So it's like an end zone.
Yeah.
Get it? Get it? Get it? Okay, show me for this graph, exo or endo. Very good. If you showed me endo, you would put red. Good. Okay. Your value for delta H should be 60. Products minus reactants, and the value for that activation energy should be 100. Any questions on interpreting these graphs?
Yes.
Okay. Yeah, we're gonna call that. Okay, we're just going to now practice it because I want to give you enough time that you shouldn't have any homework over fall.
Is that what the homework is? Like doing that?
Pretty much. Pretty much.
Is that?
Yeah, that's what it looks like. Okay, so this is your homework packet. I'll pass out to you. The homework that we're working on right now is just the very first one. Okay, it says reaction, energy, and rate, front and back are what you need to do though. Okay? Once again, there should be plenty of time to get this done in class, so you don't have to do it over Thanksgiving break. Okay? If you get this done before the bell rings, I would then highly recommend that you work on anything you're missing. Okay, particularly from the purple packet because that is due tomorrow is when all of those are due in the purple packet. So if you're missing any of that, I'd work on that. If not, you could also start working on test or quiz corrections for the last quiz if you're wanting to do that too. Okay, but do this homework first so we can make sure we understand these graphs and things, okay?
Oh, sorry, it's like a slash for the one.
So, do we have school Monday?
And then that's a parenthesis. Yes.
So that's what I'll see you
No,
guys.
no, no.
When will you see this again?
Next Monday.
We're clear.
Oh, just in one?
Nightmare.
It's the slash. Oh wait, we're not doing that.
Why is that next?
I don't like PD.
I didn't know.
The only thing I have.
Oh.
Me neither.
Well, this week it's only one, so.
That was just
I associate with a slow day.
Yeah.
That happened.